Welcome to lecture number 7 of HVDC transmission system. In this lecture, we learn about the inverter operation of HVDC transmission system. So, in previous lecture, we learned the rectifier operation and we derived some expression of rectifier operation. Right? We derive one expression VD is equal to VDO cos alpha minus RCID. This is your final DC output voltage in the rectifier operation, where RC is equal to 3 upon pi XC. We also derive one expression from this if we consider the delta angle, right? What is delta? So delta is equal to alpha plus mu. So if we consider the delta angle in the rectifier operation, so at that time our equation becomes VD is equal to VDO cos delta plus RCID. Or you can also write out VDO cos in bracket alpha plus mu plus RCID. So these all are equations are used for a rectifier operation. So now if we perform the inverter operation or if we calculate the DC output voltage in the inverter operation, and if there is no commutation overlap at that time, your DC output voltage VD is equal to VDO cos alpha. There is no overlapping, right? And therefore the VD reverse and the alpha is equal to 90 degree. So with overlap, your VD is equal to VDO cos alpha minus del VD. So also we know the value of del VD, right? What is the value of del VD? So del VD, the change in the DCR voltage is equal to the VDO by 2 cos alpha minus cos delta. We already derived this equation. So put this value of del VD in equation number 1. So you will get VD is equal to VDO cos alpha minus del VD, it is VDO by 2 cos alpha minus cos delta. If we solve this equation, your DC output voltage is equal to VDO by 2 cos alpha plus cos delta. So the value of alpha t from beyond which the inversion takes place is given by cos alpha t plus cos delta t is equal to 0. So we can write also alpha t plus delta t cos inverse 0, it is pi, and therefore we write alpha t is equal to pi minus delta t. Or also what is delta t? It is alpha plus mu, so you can write pi minus alpha plus mu means alpha t minus mu. So it is pi minus mu by 2. So your alpha t is equal to pi minus mu by 2. alpha t is equal to pi minus mu by 2. So the effect of the overlap is thus to reduce alpha t from 90 to 90 minus mu by 2. So for the successful communication, the changeover from the outgoing valve to the incoming valve must be complete before the commutating voltage becomes negative. So for example, if your commutation from valve 1 to valve 3 is possible only when the EB is more positive than EA. Now what is EB? It is a phase voltage phase voltage of B, and EA, it is a phase voltage of A, and therefore the current changeover from valve 1 to the valve 3 must be complete before EA becomes more positive than EB with sufficient margin to allow for the value deionization. So for inverter operation, we can write the new angle beta, it is equal to pi minus alpha, or it is called the ignition advance angle. Ignition advance angle. The another angle, it is called the mu, is equal to gamma, it is equal to pi minus delta. It is called extinction advance angle. And the mu is equal to delta minus alpha is equal to beta minus gamma is equal to your overlap angle in inverter operation. So therefore, we can write here the cos alpha is equal to, what we write? The cos over here, cos pi minus beta. So cos pi minus beta is equal to minus cos beta, and cos delta, it is pi minus gamma. So pi minus gamma is minus cos gamma. So we can substitute the value of cos alpha and cos delta, this value, in this equation. So we can get the equation of the inverter operation. Also, we know for rectifier operation, the value of DC current, it is given by ID is equal to root 3 EM divided by 2 omega LC multiplied by cos alpha minus cos beta. So we can write, it is called the IS2, this term is called the IS2, right? So it is IS2 cos alpha minus cos beta. So put the value of cos alpha is equal to cos beta, and cos delta is equal to minus cos gamma. It is cos delta. Cos delta. Right. This is also cos delta. So put the value of cos alpha equal to minus cos beta, and cos delta gives minus cos gamma. For the inverter operation, for inverter operation, your value of DC current, which is ID, is equal to IS2 into bracket cos gamma minus cos beta. Similarly, for rectifier operation, we also already write one equation, Vd is equal to Vdu by 2 cos alpha plus cos delta, right? So again put the value of cos alpha is equal to minus cos beta and cos beta is equal to minus cos gamma. So this equation, this is for rectifier. So this equation is become is equal to VDO by 2 what, cos gamma plus cos beta, right, for inverter. This minus VD it is called the, it is in reverse direction, right? Therefore this can become a minus VD is equal to VDO by 2 cos gamma plus cos beta. And this equation, right, VD is equal to VDO cos alpha minus RCID, put the value of cos alpha is equal to minus cos beta. And in this equation, VD is equal to VDO cos delta plus RCID. In that, put the cos delta is equal to minus cos gamma. So these two equations is now become VD is equal to VDO cos beta plus RCID. This is your new equation for inverter operation. Similarly, again more equation of DC output voltage. It is equal to VDO cos gamma minus RCID. So these all are equations which we use during the for solving the inverter operation examples. So now your inverter operation equivalent circuit, if we consider the in terms of beta, it's become like this one. This is your resistor, this is your DC source, so what, it is a change in the DC source, so this is that. So this is your RC. Here the current is flowing ID. If we supply the voltage is VDI, and this one is called the VDO cos beta. This is the equivalent circuit for an inverter operation if it comes in terms of beta. Similarly, if we take the gamma at that time, your equivalent circuit is, this is your resistor, this is your source, and now this term is become minus RC, and this is your VDO cos gamma, and this is your supply voltage VDI, and at the time the current is flowing is ID. So these two are the inverter equivalent circuit with VDI positive. This is in terms of gamma and this is in terms of beta. Thank you.